Picture this, a force so powerful, it's pulling entire galaxies toward it, including our own Milky Way. Yet, it's hidden from view, tucked behind a curtain of cosmic dust and stars. This isn't science fiction, it's the Great Attractor, one of the universe's most enigmatic mysteries. But what exactly is it, and why does it wield such an irresistible gravitational pull? Right now, we're about to embark on a journey into the heart of space's largest structures, where the Great Attractor reigns supreme. Along the way, we'll uncover secrets that challenge everything we think we know about the cosmos. From the role of dark matter to the cosmic web's intricate design, this is a story of discovery, wonder, and unanswered questions. So, get ready to explore the universe like never before, because by the end of this video, you'll see the Great Attractor and the vast structures around it in a whole new light. Let's dive in. Now, let's begin our exploration with the first secret, the Great Attractor's hidden location. Imagine trying to find something that's not only incredibly far away, but also hidden behind a thick wall of cosmic material. That's exactly the challenge astronomers face when studying the Great Attractor. It lies behind what's known as the galactic plane of the Milky Way, a dense region filled with stars, dust, and gas. This area, often referred to as the zone of avoidance, acts like a cosmic blind spot, blocking our view of anything behind it. For decades, this has made the Great Attractor one of the most elusive objects in the universe. Despite advances in technology, peering through this obscuring layer remains a significant challenge. Yet, this very difficulty has fueled our curiosity, driving astronomers to develop innovative techniques to uncover what lies beyond. So, while the Great Attractor's location has kept it shrouded in mystery, it's also inspired some of the most groundbreaking discoveries in modern astronomy. Now, turning to the next mystery, let's dive into the cosmic tug-of-war caused by the Great Attractor. This massive structure isn't just sitting quietly in the universe, it's actively pulling galaxies toward it with an almost irresistible gravitational force. Picture this, our Milky Way, along with countless other galaxies, is being drawn toward the Great Attractor as if caught in a cosmic current. This movement isn't random. It's a direct result of the immense gravitational pull exerted by this mysterious region. But here's where it gets even more fascinating. The Great Attractor's influence challenges some of our fundamental ideas about how the universe works. For instance, the way galaxies are moving toward it doesn't always align with what we'd expect based on the distribution of visible matter. This discrepancy has led scientists to question whether there's more to the story, perhaps involving dark matter or other unseen forces. So, while the Great Attractor's gravitational pull is shaping the motion of galaxies on a grand scale, it's also reshaping our understanding of cosmic dynamics, leaving us with even more questions to explore. As we venture deeper into the mystery, let's explore the role of dark matter in the Great Attractor's gravitational influence. While the Great Attractor's pull is undeniable, scientists have long struggled to explain its immense power solely based on the visible matter we can observe. This is where dark matter enters the picture. Dark matter, an invisible and mysterious substance that doesn't emit light or energy, is believed to make up a significant portion of the universe's total mass. It's thought to form an invisible scaffold around galaxies and large-scale structures, including the Great Attractor. Here's the twist: the gravitational pull we're witnessing might not just come from the galaxies we see, but from the vast amounts of dark matter surrounding and permeating the Great Attractor. This theory could explain why the observed motions of galaxies don't always match predictions based on visible matter alone. Some researchers suggest that dark matter acts as a hidden force multiplier, amplifying the Great Attractor's gravitational influence on a cosmic scale. If this is true, it would mean that dark matter isn't just a passive bystander but an active player in shaping the universe's large-scale structure. As we continue to study this enigmatic force, one thing is clear: dark matter might hold the key to unlocking the secrets of the Great Attractor and its extraordinary power over the cosmos. Now turning to the connection between the Great Attractor and the Shapley Supercluster, we uncover a fascinating piece of the cosmic puzzle. The Shapley Supercluster is the largest known concentration of galaxies in the observable universe, a massive structure located hundreds of millions of light-years away. What makes this relationship intriguing is that the Shapley Supercluster's immense gravitational pull is thought to influence the Great Attractor itself. Scientists believe that the Great Attractor is not acting alone in drawing galaxies toward it. Instead, it's part of a larger gravitational dance. The Shapley Supercluster's pull may be amplifying the Great Attractor's effect, adding another layer of complexity to this cosmic mystery. This connection raises questions about how these massive structures interact and shape the flow of galaxies across the universe. Some researchers suggest that the Great Attractor could even be a local manifestation of the Shapley Supercluster's far-reaching influence. This interplay between these colossal structures challenges our understanding of gravity on the largest scales and deepens the enigma of the Great Attractor. As we explore this relationship further, we're reminded that the universe's secrets are often hidden in the connections between its most awe-inspiring phenomena. Now shifting our focus to the peculiar behavior of galaxies drawn toward the Great Attractor, we encounter yet another layer of cosmic intrigue. Galaxies in the vicinity of the Great Attractor are moving at speeds that defy expectations, a phenomenon astronomers refer to as velocity anomalies. Normally, galaxies follow predictable paths dictated by the expansion of the universe and local gravitational influences. Yet, in this case, galaxies are racing toward the Great Attractor at velocities that can't be fully explained by visible matter alone. This has left scientists scratching their heads for decades. What's driving this unusual motion? One leading theory points to the presence of vast amounts of dark matter, unseen but exerting a powerful gravitational pull. Another possibility is that the Great Attractor's influence is amplified by even larger structures, like the Shapley Supercluster, creating a cosmic tug-of-war that accelerates galaxies beyond normal speeds. This velocity anomaly not only deepens the mystery of the Great Attractor, but also challenges our understanding of how gravity operates on the grandest scales. As astronomers continue to study these peculiar motions, they're uncovering clues that could reshape our knowledge of the universe's structure and the forces that govern it. This puzzle reminds us that even in the cosmos, the most unexpected phenomena often hold the keys to unlocking its deepest secrets. Now shifting our gaze to the grand tapestry of the universe, we uncover the Great Attractor's place within the cosmic web. This intricate structure, composed of vast filaments of galaxies and immense voids, serves as the scaffolding of the cosmos. The Great Attractor doesn't act alone, it's a single node within this sprawling network. These filaments, made up of dark matter and galaxies, act like highways, guiding the movement of matter across the universe. The voids, on the other hand, are vast, empty regions that shape the distribution of galaxies and clusters. Together, they create the universe's large-scale structure, with the Great Attractor playing a pivotal role in this cosmic dance. Understanding its place within the web helps us see how it influences not just nearby galaxies but the broader flow of matter. This connection highlights the Great Attractor as a key player in the universe's architecture, reminding us that even the most massive structures are interconnected parts of a much larger whole. Now turning to the sheer magnitude of the Great Attractor, let's try to wrap our minds around its size and scale. To put it simply, the Great Attractor is enormous. It spans a region of space that's hundreds of millions of light-years across, pulling in galaxies with its immense gravitational force. To give you a sense of its scale, imagine the Milky Way. Our galaxy is vast, measuring about 100,000 light-years in diameter. Yet, the Great Attractor dwarfs it, encompassing thousands of galaxies within its influence. But it doesn't stop there. When we compare it to other colossal structures in the universe, like the Shapley Supercluster, the Great Attractor holds its own as one of the most massive gravitational focal points we've observed. These structures are so vast that they challenge our ability to comprehend their size. To visualize it, picture a cosmic ocean with islands of galaxies, and the Great Attractor is one of the largest islands, drawing everything toward it. Its scale not only highlights its power, but also underscores its role in shaping the universe's large-scale structure. As we explore its size, we begin to grasp just how significant this mysterious force is in the grand scheme of the cosmos. Now shifting our focus to the origins of the Great Attractor, let's dive into one of its most intriguing mysteries. How did it form? Scientists have proposed several theories to explain its existence, each offering a fascinating glimpse into the forces that shape the universe. One leading idea is that the Great Attractor emerged during the early stages of cosmic inflation, a period of rapid expansion just after the Big Bang. During this time, tiny fluctuations in density grew into the massive structures we see today, with the Great Attractor being one of the most prominent. Another key factor in its formation is gravitational collapse, where matter in the universe clumped together over billions of years, pulled by its own gravity. Think of it like a cosmic snowball effect, where small accumulations of matter grew into immense gravitational hubs. Some researchers also suggest that the Great Attractor's location at the intersection of multiple cosmic filaments played a crucial role, funneling matter into a concentrated region. These theories not only help us understand its formation, but also shed light on how large-scale structures evolve over time. By exploring these ideas, we get closer to unraveling the secrets of the Great Attractor and its place in the cosmic story. Now looking ahead, let's explore the future of the Great Attractor and the galaxies caught in its gravitational grip. Over billions of years, its immense pull will continue to shape the motion of countless galaxies, including our own Milky Way. One theory suggests that as the universe expands, the Great Attractor's influence may weaken, allowing galaxies to drift apart over time. However, others believe that its gravitational dominance could lead to a cosmic collision, with galaxies merging into a single, massive structure. Some scientists speculate that the Great Attractor might eventually become part of an even larger supercluster as it continues to draw in surrounding matter. Another intriguing possibility is that dark energy, the mysterious force driving the universe's accelerated expansion, could counteract the Great Attractor's pull, altering its trajectory and impact. These scenarios highlight the dynamic nature of our universe, where forces like gravity and dark energy shape the fate of celestial bodies. By studying the Great Attractor's future, we gain valuable insights into the long-term evolution of the cosmos, offering a glimpse of what lies ahead in the vast expanse of space. Now shifting our focus closer to home, let's examine how the Great Attractor influences the galaxies in our cosmic neighborhood. Among the most notable are the Milky Way and Andromeda, both of which are being drawn toward this mysterious gravitational powerhouse. The Milky Way, our home galaxy, is hurtling through space at an astonishing speed of over 600 kilometers per second, pulled inexorably toward the Great Attractor. This motion isn't just a straight line, though. Our galaxy is also engaged in a delicate dance with Andromeda, its nearest neighbor, as both are drawn toward the same cosmic destination. Scientists predict that in about 4 billion years, the Milky Way and Andromeda will collide, merging into a single, larger galaxy. But even this dramatic event is just one part of a much larger journey, as the newly formed galaxy will continue to be tugged toward the Great Attractor. This ongoing gravitational influence has profound implications for the future of our local group of galaxies. As they move closer to the Great Attractor, their trajectories could intersect with other galaxy clusters, leading to further collisions and mergers. This process of cosmic evolution, driven by the Great Attractor's pull, highlights how interconnected the universe truly is. By studying these local effects, we gain a deeper understanding of the forces shaping our galaxy's path and the ultimate fate of the stars and planets within it. Now delving deeper into the fabric of the cosmos, let's explore the Great Attractor's fascinating relationship with the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light, first discovered in 1964, serves as a snapshot of the universe when it was just 380,000 years old. The cosmic microwave background is not perfectly uniform. Instead, it contains tiny fluctuations in temperature, which are essentially the seeds of all the large-scale structures we see today, including the Great Attractor. Scientists have observed that the Great Attractor's immense gravitational pull causes subtle distortions in this background radiation, a phenomenon known as the integrated Sachs-Wolf effect. These distortions reveal how the Great Attractor's gravity bends the path of light from the early universe, leaving an imprint on the cosmic microwave background. By studying these distortions, astronomers can map the distribution of matter, including dark matter, in the region of the Great Attractor. This provides crucial insights into the universe's structure and evolution. Furthermore, these observations help us understand how the Great Attractor formed and how it has influenced the growth of cosmic structures over billions of years. The cosmic microwave background acts like a cosmic fingerprint, allowing us to trace the origins of the Great Attractor and its role in shaping the universe as we know it. This connection between the Great Attractor and the cosmic microwave background not only deepens our understanding of the early universe, but also highlights the intricate interplay between gravity, matter, and light on the grandest scales. Now shifting our gaze closer to our cosmic neighborhood, let's uncover the hidden galaxies lurking behind the Milky Way's veil of dust and gas, galaxies that play a crucial role in the Great Attractor's gravitational influence. Our galaxy's thick disk of dust and gas, known as the zone of avoidance, has long obscured our view of the universe in this direction. But thanks to advancements in technology, particularly infrared and radio telescopes, astronomers are now able to peer through this cosmic haze and reveal the galaxies hidden within. These telescopes detect wavelengths of light that can pass through the Milky Way's dust, allowing scientists to map out regions previously invisible to us. What they've discovered is astonishing, a rich tapestry of galaxies, some of which are massive and densely packed, contributing significantly to the Great Attractor's pull. One of the most notable discoveries is the Norma Cluster, a massive group of galaxies located near the center of the Great Attractor's influence. This cluster alone contains hundreds of galaxies, each adding to the overall gravitational tug. Additionally, surveys like the 2-micron All-Sky Survey have revealed thousands of previously unknown galaxies in this region, shedding light on the true scale of the Great Attractor's domain. Astronomers are also using techniques like redshift measurements to determine the distances and velocities of these hidden galaxies, helping to piece together how they interact with the Great Attractor. These findings not only deepen our understanding of the Great Attractor's structure, but also highlight the incredible ingenuity of modern astronomy in overcoming observational challenges. As we continue to uncover these hidden realms, we gain a clearer picture of the cosmic forces shaping our universe. Now delving into the enigmatic phenomenon known as dark flow, we uncover another layer of the Great Attractor's cosmic influence. Dark flow refers to the puzzling observation that certain galaxy clusters seem to move in a specific direction, almost as if being pulled by an unseen force. This motion is distinct from the universe's overall expansion, suggesting the presence of something massive and mysterious exerting its gravitational pull beyond the observable universe. Astronomers first detected this strange movement while studying the cosmic microwave background, the afterglow of the Big Bang. They noticed that these galaxy clusters were not just expanding with the universe, but also drifting in unison toward a particular region of space. This alignment has led researchers to speculate that the Great Attractor, or perhaps something even more immense lying beyond it, could be the source of this dark flow. Some theories propose that the Great Attractor itself might be part of a much larger structure, such as a supercluster or a vast concentration of matter, whose gravitational reach extends far beyond what we can currently observe. While the exact nature of dark flow remains a mystery, its potential connection to the Great Attractor opens up exciting possibilities for understanding the forces that shape our universe on the grandest scales. As astronomers continue to study this phenomenon, they hope to uncover whether the Great Attractor is a mere player in this cosmic tug-of-war or the key to unlocking one of the universe's deepest secrets. Shifting our focus to another cosmic puzzle, let's examine how the Great Attractor might be influencing one of the most fundamental measurements in cosmology, the Hubble constant. The Hubble constant represents the rate at which the universe is expanding, a number that helps us understand the age, size, and future of the cosmos. However, measuring this constant accurately has proven to be a challenging task, with different methods yielding slightly different results. One factor that could be complicating these measurements is the immense gravitational pull of the Great Attractor. As galaxies are drawn toward this mysterious region, their motions are not solely governed by the universe's expansion, but also by the Great Attractor's influence. This additional force can distort the apparent velocities of galaxies, making it harder for astronomers to isolate the true rate of cosmic expansion. Some researchers suggest that the Great Attractor's gravitational effects could be introducing a local anomaly, skewing our measurements of the Hubble constant in ways we're only beginning to understand. By accounting for this gravitational tug, scientists hope to refine their calculations and resolve the discrepancies between different measurement techniques. This connection between the Great Attractor and the Hubble constant not only highlights the complexity of our universe, but also underscores the importance of considering local cosmic forces when interpreting global phenomena. As we continue to study this interplay, we edge closer to unraveling one of cosmology's most persistent mysteries and gaining a clearer picture of how our universe evolves. Now turning to the Great Attractor's impact on the life cycle of galaxies, let's explore how this mysterious force shapes the evolution of stars and galaxies across the cosmos. The gravitational pull of the Great Attractor doesn't just tug galaxies toward it, it also plays a crucial role in their development. As galaxies are drawn into its orbit, they experience increased interactions with neighboring galaxies. These encounters can trigger bursts of star formation, as the gravitational forces compress gas and dust within galaxies, igniting the birth of new stars. At the same time, the Great Attractor's influence can lead to galaxy mergers, where two or more galaxies collide and combine over millions of years. These mergers are pivotal events in galactic evolution, as they reshape the structure of galaxies, often forming larger, more complex systems. For example, elliptical galaxies, which are typically more massive and featureless, are thought to be the result of such mergers. The gravitational interactions driven by the Great Attractor can also strip galaxies of their gas, halting star formation and leading to the creation of so-called red and dead galaxies where star birth has ceased entirely. This dynamic process highlights the Great Attractor's dual role as both a creator and a destroyer in the cosmic landscape. By studying these effects, astronomers gain insights into how galaxies evolve over time and how large-scale structures like the Great Attractor shape the universe we see today. As we continue to unravel its mysteries, we uncover not just the secrets of the Great Attractor itself, but also the broader story of how galaxies grow, change, and interact in the vast tapestry of the cosmos. As we delve deeper into the enigmatic Great Attractor, we now shift our focus to a fascinating aspect of its nature, its X-ray emissions. These high-energy signals provide a unique window into the structure and composition of this cosmic giant. When astronomers first detected X-rays emanating from the region of the Great Attractor, it was a significant breakthrough. Unlike visible light, which is obscured by the Milky Way's dust and gas, X-rays can penetrate this barrier, offering a clearer view of what lies beyond. The emissions are primarily produced by extremely hot gas, reaching temperatures of millions of degrees, which fills the vast space between galaxies in the Great Attractor's vicinity. This hot gas is a key component of the intergalactic medium, the material that exists between galaxies. By studying the intensity and distribution of these X-rays, scientists can map the density and structure of this gas, revealing how it's spread across the Great Attractor. More importantly, the hot gas helps astronomers estimate the total mass of the Great Attractor, including both visible matter and the elusive dark matter that makes up a significant portion of its gravitational pull. These findings have also shed light on the dynamics of galaxy clusters within the Great Attractor's influence, showing how the hot gas interacts with galaxies and contributes to their evolution. As we continue to analyze these X-ray emissions, we gain not only a better understanding of the Great Attractor itself, but also a deeper insight into the large-scale processes that shape the universe. This invisible light, invisible to our eyes, has become one of the most powerful tools in our quest to unravel the mysteries of the cosmos. Now shifting our focus to the heart of the Great Attractor, let's explore a captivating theory, the possibility of a supermassive black hole at its core. This idea has sparked intense debate among astronomers, as such a black hole could explain the immense gravitational force pulling entire galaxies toward this mysterious region. Supermassive black holes are already known to lurk at the centers of most galaxies, including our own Milky Way. These cosmic giants can weigh billions of times more than the Sun, exerting a gravitational influence that shapes the evolution of their host galaxies. If the Great Attractor harbors a supermassive black hole, it would likely be one of the most massive ever discovered, given the scale of its gravitational pull. One piece of evidence supporting this theory is the behavior of galaxies within the Great Attractor's vicinity. Their rapid movement and clustering suggest the presence of an extraordinarily dense and massive object at the center. Additionally, the hot gas detected through X-ray emissions could be heated by the intense gravitational forces near a supermassive black hole, as matter spirals inward and releases energy. However, not all observations align with this idea. For instance, the distribution of matter in the Great Attractor doesn't match the typical pattern seen around known supermassive black holes. Some scientists argue that the gravitational force might instead be the result of a massive concentration of dark matter or the combined pull of countless galaxies in the region. While the supermassive black hole theory remains unproven, it continues to intrigue researchers as they gather more data. Whether or not such a black hole exists, exploring this possibility deepens our understanding of the forces shaping the universe and the incredible phenomena hidden within it. As our journey through the secrets of the Great Attractor continues, the next mystery awaits, shedding even more light on this cosmic enigma. Now, stepping into the vast emptiness that envelops the Great Attractor, we uncover another layer of its cosmic intrigue. This mysterious region isn't just a gravitational powerhouse, it's also bordered by immense cosmic voids, vast stretches of space that are nearly empty of matter. These voids, some spanning hundreds of millions of light years, create a stark contrast to the dense clusters of galaxies within the Great Attractor's reach. The presence of these voids plays a crucial role in shaping the Great Attractor's influence. Imagine the universe as a patchwork quilt, with dense regions of galaxies stitched together by threads of dark matter and enormous empty spaces in between. The Great Attractor sits at the edge of one such void, and this unique positioning amplifies its gravitational pull. The lack of matter in the voids means there's less gravitational resistance, allowing the Great Attractor's force to extend farther and with greater intensity. This dynamic also affects the movement of galaxies. As galaxies on the fringes of these voids are drawn toward the Great Attractor, they experience a kind of cosmic vacuum effect. The emptiness of the voids creates a low-pressure zone, so to speak, pulling galaxies inward as if they were being sucked into a gravitational current. This phenomenon helps explain why galaxies over such vast distances are being drawn toward the Great Attractor, even from regions that seem impossibly far away. But the relationship between the Great Attractor and the cosmic voids isn't just one way. The voids themselves are shaped by the presence of massive structures like the Great Attractor. As matter is pulled into these dense regions, it leaves behind the empty spaces we observe as voids. This interplay between density and emptiness is a key feature of the universe's large-scale structure, and the Great Attractor is at the heart of this cosmic dance. As we continue to explore the mysteries of the Great Attractor, the surrounding voids remind us that even in the vastness of space, emptiness plays a vital role in shaping the universe. The next secret we uncover will further illuminate how this enigmatic force continues to shape the cosmos. Now shifting our gaze closer to home, we find the Great Attractor's influence extending to the Virgo Supercluster, the sprawling cosmic neighborhood that includes our own Milky Way and its surrounding galaxies. This supercluster, one of the most massive structures in our local universe, is composed of thousands of galaxies bound together by gravity. It's like a bustling city of stars and planets with the Virgo cluster at its heart. But what's truly fascinating is how the Great Attractor interacts with this colossal network. The Virgo Supercluster and the Great Attractor are not isolated entities. They're deeply interconnected in the cosmic dance of gravity. While the Virgo Supercluster exerts its own gravitational pull, the Great Attractor's immense force adds another layer to this dynamic. Scientists have observed that the galaxies within the Virgo Supercluster are not just moving randomly, they're also being subtly tugged toward the Great Attractor. This dual influence creates a complex interplay of forces, shaping the trajectories of galaxies on an unimaginable scale. Interestingly, the Milky Way and its nearby galaxies, including Andromeda, are part of a smaller group called the Local Group, which itself is a tiny fraction of the Virgo Supercluster. The Great Attractor's gravitational pull affects not just the Virgo Supercluster as a whole, but also the local group within it. This means that even our own galaxy is caught in this cosmic tug-of-war, slowly drifting toward the Great Attractor over billions of years. But the relationship goes both ways. Just as the Great Attractor influences the Virgo Supercluster, the supercluster's massive presence also contributes to the overall gravitational landscape. The combined mass of its thousands of galaxies creates a gravitational field that interacts with the Great Attractor's own pull, adding complexity to the way galaxies move and evolve. This mutual interaction is a perfect example of how the universe's large-scale structures are interconnected, each one shaping and being shaped by the others. As we continue to explore the Great Attractor's secrets, its relationship with the Virgo Supercluster reminds us that even in the vastness of space, no structure exists in isolation. Everything is part of a larger cosmic web, where gravity weaves galaxies, superclusters, and even the voids between them into a single, intricate tapestry. The next secret will further unravel how these interactions shape the universe on an even grander scale. Now shifting our focus to the broader universe, let's explore how the Great Attractor plays a role in the grand drama of cosmic expansion. The universe has been expanding since the Big Bang, with galaxies moving away from each other as space itself stretches. But this expansion isn't uniform everywhere. In regions dominated by massive structures like the Great Attractor, gravity can slow down or even counteract this expansion on a local scale. The Great Attractor's immense gravitational pull creates what scientists call a cosmic tug-of-war. On one side, there's the relentless force of dark energy, which drives the universe's accelerated expansion. On the other side, there's gravity, the force that pulls matter together. In the vicinity of the Great Attractor, gravity temporarily takes the upper hand, bending the trajectories of galaxies and clusters toward it. This creates a fascinating balance between the forces pushing the universe apart and those pulling it together. Interestingly, this tug-of-war isn't just a local phenomenon. The Great Attractor's gravitational influence ripples across vast distances, affecting the motion of galaxies far beyond its immediate neighborhood. While dark energy still dominates on the largest scales, ensuring the universe continues to expand, the Great Attractor reminds us that gravity remains a powerful player in shaping the cosmos. This interplay between expansion and gravitational pull also has implications for how we measure the universe's growth. The Hubble constant, which describes the rate of cosmic expansion, can appear to vary slightly depending on where we look. In regions influenced by massive structures like the Great Attractor, the expansion rate might seem slower due to the competing pull of gravity. This adds another layer of complexity to our understanding of the universe's evolution. As we ponder the Great Attractor's impact on cosmic expansion, we're reminded that the universe is a dynamic and ever-changing place. Forces both seen and unseen are constantly at work, shaping the fabric of space and time in ways we're only beginning to understand. This cosmic tug-of-war is just one of the many mysteries that make the Great Attractor a cornerstone of modern cosmology. Now turning to the enigma of the Great Attractor's hidden mass, we find ourselves facing one of the most puzzling questions in modern cosmology. Just how much matter is packed into this colossal structure, and how do astronomers even begin to measure it? The answer isn't straightforward. The Great Attractor's mass isn't something we can simply weigh on a cosmic scale. Instead, scientists rely on indirect methods, such as observing the motion of galaxies and clusters that are being pulled toward it. The faster these galaxies move, the stronger the gravitational influence, and by extension, the greater the mass of the Great Attractor. However, this approach comes with its own set of challenges. For one, the Great Attractor is partially hidden behind the dense band of stars, gas, and dust in our own Milky Way, making direct observations difficult. This so-called zone of avoidance obscures a significant portion of the Great Attractor's region, leaving astronomers to piece together its mass from incomplete data. Additionally, the Great Attractor isn't a single, isolated object but part of a complex web of galaxies, clusters, and dark matter. Untangling the gravitational contributions of these components is no easy task. Another complication arises from the presence of dark matter, which makes up a substantial portion of the Great Attractor's mass. Unlike normal matter, dark matter doesn't emit light or interact with electromagnetic forces, making it invisible to traditional telescopes. Scientists must infer its presence through its gravitational effects, adding another layer of uncertainty to mass calculations. Despite these hurdles, astronomers have made significant progress. Current estimates suggest the Great Attractor's mass could be equivalent to tens of thousands of galaxies, with some studies pointing to a figure in the range of several quadrillion times the mass of our Sun. Yet, even with these estimates, the true scale of the Great Attractor remains shrouded in mystery. As we continue to explore this cosmic giant, one thing is clear: the Great Attractor's hidden mass is a testament to the complexity of the universe. It challenges our understanding of gravity, dark matter, and the large-scale structure of the cosmos. And as technology advances and new observations emerge, we may finally uncover the secrets of this gravitational behemoth. Now shifting our focus to the Great Attractor's role in shaping galaxy clusters, we uncover yet another layer of its cosmic influence. Galaxy clusters are some of the largest structures in the universe, bound together by gravity, and the Great Attractor plays a significant part in their formation and movement. Its immense gravitational pull doesn't just affect individual galaxies, it also dictates the behavior of entire clusters, drawing them toward its center and influencing their trajectories through space. The gravitational force exerted by the Great Attractor can cause galaxy clusters to merge, creating even larger structures. These mergers are not just cosmic collisions but transformative events that shape the evolution of galaxies within them. As clusters are pulled toward the Great Attractor, they collide, triggering bursts of star formation and the growth of supermassive black holes. These interactions are key to understanding how galaxy clusters evolve over billions of years. Moreover, the Great Attractor's influence extends to the distribution of galaxy clusters in its vicinity. Clusters don't move randomly through space but follow the gravitational pathways created by the Great Attractor's pull. This motion creates a kind of cosmic flow where clusters and galaxies are funneled toward the same region, contributing to the large-scale structure of the universe. Interestingly, the Great Attractor's role isn't limited to attracting galaxy clusters. It also helps define the boundaries of cosmic voids. These vast, empty regions of space are surrounded by dense clusters of galaxies, and the Great Attractor's gravitational pull contributes to this intricate balance. By influencing the movement of galaxy clusters, it helps shape the web-like structure of the cosmos, where filaments of galaxies crisscross vast voids. As we delve deeper into the Great Attractor's impact on galaxy clusters, we gain a clearer picture of its role in the universe's grand design. It's not just a gravitational anomaly but a key player in the evolution of large-scale structures, shaping the destiny of galaxies and clusters alike. This cosmic interplay between attraction and structure reminds us of the complex and beautiful forces at work in the universe, driving its endless transformation. Now turning to the Great Attractor's connection to the Big Bang, we uncover a fascinating link between this mysterious cosmic force and the birth of the universe itself. The Big Bang, the event that set the cosmos into motion over 13 billion years ago, created a universe filled with energy, matter, and the seeds of structures like the Great Attractor. As the universe expanded, tiny fluctuations in density grew over time, eventually giving rise to the massive clusters and filaments we see today. The Great Attractor, with its immense gravitational pull, may have its origins in these early density variations, making it a direct descendant of the Big Bang's conditions. The conditions of the early universe were crucial in shaping the distribution of matter on a grand scale. As matter clumped together under gravity, regions of higher density began to attract more matter, forming the foundations of structures like the Great Attractor. This process, driven by the initial conditions set by the Big Bang, suggests that the Great Attractor isn't just a random occurrence but a natural outcome of the universe's evolution. Its existence provides a window into how the seeds of the Big Bang grew into the vast cosmic structures we observe today. Another intriguing aspect is the role of dark energy, the force driving the universe's accelerated expansion. While the Big Bang set the universe in motion, dark energy has influenced how structures like the Great Attractor have evolved over time. The interplay between the gravitational pull of the Great Attractor and the expansive force of dark energy creates a dynamic cosmic landscape where the remnants of the Big Bang continue to shape the universe's large-scale structure. By studying the Great Attractor, scientists gain insights into the universe's earliest moments. Its gravitational influence and the way it interacts with surrounding galaxies and clusters offer clues about the initial conditions of the Big Bang. In this way, the Great Attractor serves as a cosmic time capsule, preserving information about the universe's origins and its ongoing transformation. As we explore its connection to the Big Bang, we deepen our understanding of how the universe began and how it continues to evolve, revealing the intricate links between the past and the present. Now moving deeper into the Great Attractor's influence, we turn our attention to its impact on the Milky Way's motion through space. The Milky Way, our home galaxy, is not stationary but is instead hurtling through the cosmos at an astonishing speed. And a significant part of this motion is directed toward the Great Attractor, whose immense gravitational pull is drawing us closer, along with thousands of other galaxies. This cosmic tug is reshaping the trajectory of our galaxy, creating a fascinating interplay of forces that will shape its future in profound ways. The Milky Way's journey is influenced by a combination of gravitational forces, with the Great Attractor playing a starring role. While our galaxy is also being pulled toward other massive structures like the Shapley Supercluster, the Great Attractor's proximity and power make it a dominant factor in our motion. This gravitational dance isn't just a simple pull. It's a complex interaction that involves the Milky Way's velocity, the expansion of the universe, and the opposing forces of dark energy. Together, these elements create a dynamic and ever-changing path for our galaxy. What does this mean for the Milky Way's future? As we continue to move toward the Great Attractor, we're not just drifting aimlessly but are part of a larger cosmic migration. Over billions of years, this movement could lead to dramatic changes in our galaxy's structure and environment. For instance, the Milky Way could eventually merge with other galaxies in the Great Attractor's influence, leading to new star formation and reshaped galactic landscapes. While this process unfolds on a timescale far beyond human lifespans, it's a reminder of the interconnectedness of the universe and the forces that shape our existence. The study of the Milky Way's motion also provides valuable insights into the distribution of matter in the universe. By tracking how our galaxy moves, scientists can map the unseen mass that drives its trajectory, including the role of dark matter. This invisible substance, which makes up a significant portion of the universe's mass, plays a crucial role in the Great Attractor's gravitational influence. Understanding how our galaxy responds to these forces helps us piece together the larger puzzle of cosmic structure and evolution. As we consider the Milky Way's journey, we're reminded that we're part of a vast, dynamic system. The Great Attractor's pull is not just a distant phenomenon but a force that shapes our galaxy's destiny. While the full story of our cosmic voyage remains to be uncovered, each discovery brings us closer to understanding the intricate forces that guide the universe. This ongoing exploration highlights the beauty and complexity of the cosmos, inviting us to look beyond our own corner of the galaxy and marvel at the grand design of the universe. Now shifting our focus to the cosmic scale, let's explore how the Great Attractor plays a crucial role in the cosmic distance ladder. This ladder is the method astronomers use to measure distances in the universe, step by step, from nearby stars to the farthest galaxies. Each rung of this ladder relies on specific techniques and objects, and the Great Attractor serves as a key marker in this intricate system. At the heart of the cosmic distance ladder is the principle of using known distances to calculate unknown ones. For example, nearby stars are measured using parallax, the apparent shift in their position as the Earth orbits the Sun. From there, astronomers use these stars to calibrate other methods, such as Cepheid variable stars, whose brightness changes in a predictable way. These Cepheids help measure distances to nearby galaxies, which in turn provide a foundation for even larger scales. The Great Attractor comes into play as astronomers study the motion of galaxies influenced by its immense gravitational pull. By observing how these galaxies move, scientists can estimate their distances using a technique called redshift. Redshift occurs when light from distant galaxies stretches as the universe expands, shifting it toward the red end of the spectrum. The amount of redshift provides a clue to the galaxy's distance, with the Great Attractor acting as a gravitational anchor in these calculations. What makes the Great Attractor particularly significant is its position in the cosmic web. As one of the largest structures in our local universe, it serves as a reference point for mapping the distribution of galaxies and understanding the universe's expansion. Its gravitational influence helps astronomers refine measurements of the Hubble constant, the rate at which the universe is expanding. By studying how galaxies move toward the Great Attractor, scientists can better calibrate the cosmic distance ladder, improving our understanding of the universe's scale and structure. The Great Attractor's role in the cosmic distance ladder also highlights the interconnectedness of cosmic phenomena. Its gravitational pull not only shapes the motion of galaxies, but also provides a framework for measuring their distances. This interplay between gravity and distance measurement underscores the complexity of the universe and the ingenuity of the methods used to explore it. As we continue to map the cosmos, the Great Attractor remains a vital piece of the puzzle. Its influence reaches far beyond its immediate surroundings, shaping our understanding of the universe's vastness and the forces that govern it. By integrating the Great Attractor into the cosmic distance ladder, astronomers gain a clearer picture of our place in the cosmos and the intricate web of connections that bind it together. This ongoing exploration reminds us that the universe is not just a collection of isolated objects, but a dynamic, interconnected system, where even the most distant structures play a role in shaping our understanding of reality. Now delving into a lesser-known aspect, let's uncover the hidden stars within the Great Attractor's vast domain. While much attention is given to its gravitational pull on galaxies, the stars nestled within its region play a crucial role in shaping its influence. These stars, often obscured by the dense dust and gas of the Milky Way's galactic plane, are not just celestial bystanders, they are integral to the Great Attractor's mass and its gravitational might. Astronomers have long struggled to observe these stars directly due to the zone of avoidance, the area of the sky where the Milky Way's brightness and dust block our view. However, advancements in infrared and radio astronomy have begun to pierce through this cosmic veil, revealing a population of stars that had remained hidden for decades. These stars, spread across the Great Attractor's region, contribute significantly to its total mass, which in turn amplifies its gravitational pull. The discovery of these hidden stars has provided new insights into the Great Attractor's structure. By mapping their distribution, scientists have been able to estimate the density of matter in this region, refining calculations of its gravitational influence. These stars, along with the galaxies and dark matter in the area, form a complex web of mass that drives the motion of nearby galaxies, including our own Milky Way. What makes these stars particularly fascinating is their role in the broader cosmic narrative. They serve as cosmic markers, helping astronomers trace the gravitational field of the Great Attractor and understand how it shapes the movement of galaxies across vast distances. By studying their light and motion, researchers can piece together the history of this mysterious region, shedding light on its formation and evolution over billions of years. The hidden stars of the Great Attractor also remind us of the universe's interconnectedness. While they may be out of sight, their presence is deeply felt through the gravitational forces they exert. This interplay between visible and hidden matter underscores the complexity of the cosmos, where even the smallest components can have a profound impact on the largest structures. As we continue to explore the Great Attractor's secrets, these hidden stars serve as a testament to the ingenuity of modern astronomy. By uncovering what lies beyond our immediate view, we gain a richer understanding of the forces that shape our universe, proving that sometimes the most significant discoveries are hidden in plain sight, or rather just beyond it. This ongoing exploration not only deepens our knowledge of the Great Attractor, but also highlights the intricate balance between the seen and unseen in the cosmos. Shifting our gaze to the broader cosmic canvas, let's explore how the Great Attractor fits into the large-scale structure map of the universe. This intricate map, often likened to a cosmic web, reveals the distribution of matter across vast distances, with the Great Attractor standing as one of its most prominent nodes. Its placement within this network is not just a matter of curiosity, it's a key to understanding the universe's architecture and evolution. The large-scale structure of the universe is shaped by gravity, which pulls matter into filaments, voids, and dense clusters. The Great Attractor, with its enormous mass, sits at the intersection of these filaments, acting as a gravitational anchor that influences the motion of galaxies across millions of light years. By mapping its position, astronomers can trace the flow of matter in our cosmic neighborhood, offering clues about how galaxies move and interact over time. One of the most striking aspects of the Great Attractor's role in this map is its relationship with other massive structures, like the Shapley Supercluster and the Virgo Supercluster. These clusters, along with the Great Attractor, form a complex hierarchy of gravitational influences that shape the universe's layout. The Great Attractor, in particular, acts as a bridge between these structures, channeling galaxies toward denser regions in an ongoing cosmic dance. Mapping the Great Attractor has also provided valuable insights into the distribution of dark matter, the invisible substance that makes up a significant portion of the universe's mass. By studying the motion of galaxies influenced by the Great Attractor, scientists can infer the presence of dark matter in its vicinity, helping to complete the cosmic jigsaw puzzle. This invisible component plays a crucial role in the universe's structure, and the Great Attractor serves as a vital clue in understanding its impact. The significance of the Great Attractor in cosmology extends beyond its immediate influence. By studying its position within the large-scale structure, researchers gain a better understanding of the universe's expansion and the forces that drive it. The Great Attractor's gravitational pull competes with the overall expansion of the cosmos, creating a dynamic interplay that shapes the evolution of galaxies and galaxy clusters. As we continue to refine our maps of the universe, the Great Attractor remains a focal point of discovery. Its role in the large-scale structure not only deepens our knowledge of the cosmos, but also highlights the interconnectedness of all matter, from the smallest particles to the largest superclusters. This ongoing exploration reminds us that the universe is far more intricate and unified than we might imagine, with the Great Attractor serving as a linchpin in our quest to understand it all. Shifting our understanding of the cosmos even further, let's now delve into how the Great Attractor's immense gravitational force might warp the very fabric of time and space itself. This phenomenon, rooted in Einstein's theory of relativity, offers a fascinating glimpse into the extreme conditions created by such a massive cosmic structure. According to Einstein, gravity isn't just a force pulling objects together. It's a curvature of space-time caused by mass. The Great Attractor, with its enormous mass, bends space-time in its vicinity, influencing not just the motion of galaxies but also the flow of time. Near the Great Attractor, the curvature of space-time would be significant enough to create observable effects. For instance, light passing near this massive structure would bend, a phenomenon known as gravitational lensing. This bending of light can distort the appearance of distant galaxies, making them appear stretched or magnified. Astronomers use this effect to study the distribution of mass in the Great Attractor's region, providing indirect evidence of its gravitational influence. Time itself would also behave differently close to the Great Attractor. According to relativity, time runs slower in stronger gravitational fields. This means that clocks near the Great Attractor would tick more slowly compared to those in regions with weaker gravity. While this effect might be subtle over short distances, it becomes more pronounced the closer one gets to such a massive gravitational source. This time dilation is a direct consequence of the warping of space-time and serves as a reminder of how gravity shapes not just space but also the passage of time. The Great Attractor's impact on space-time also has broader implications for our understanding of the universe. Its immense gravity contributes to the large-scale structure of the cosmos, influencing the paths of galaxies and the growth of galaxy clusters. By studying how the Great Attractor warps space-time, scientists can gain insights into the distribution of dark matter, the nature of gravity, and the overall evolution of the universe. This interplay between gravity, time, and space underscores the profound role the Great Attractor plays in the cosmos. Its ability to warp space-time is a testament to the extreme conditions that exist in the universe, challenging our understanding of physics and inviting us to explore the mysteries of gravity on a grand scale. As we continue to study this remarkable structure, we uncover not just the secrets of the Great Attractor, but also the deeper truths about the nature of time, space, and the universe itself. Now, as we broaden our perspective, let's explore how the Great Attractor plays a pivotal role in the grand story of cosmic evolution. This colossal structure isn't just a gravitational anomaly, it's a key player in shaping the universe as we know it. From the birth of galaxies to the intricate distribution of matter, the Great Attractor's influence is woven into the very fabric of cosmic history. At its core, the Great Attractor's immense gravitational pull acts as a cosmic sculptor, guiding the formation and movement of galaxies. As galaxies form from clouds of gas and dust, the gravitational forces exerted by structures like the Great Attractor help pull these materials together, triggering the birth of stars and galactic systems. Over billions of years, this process has led to the creation of the vast galaxy clusters we observe today, with the Great Attractor serving as a gravitational anchor in its region of the universe. But its role doesn't stop there. The Great Attractor also influences the large-scale distribution of matter across the cosmos. By pulling galaxies and galaxy clusters toward it, it helps shape the cosmic web, the intricate network of filaments and voids that defines the universe's structure. This web is not just a random arrangement, it's a direct result of the gravitational forces exerted by massive objects like the Great Attractor. Its pull ensures that matter isn't evenly distributed but instead concentrated in specific regions, creating the dense clusters and vast voids that characterize the universe's large-scale structure. Moreover, the Great Attractor's gravitational influence extends to the evolution of galaxies themselves. As galaxies are drawn toward it, they interact with one another, often merging to form larger, more complex systems. These galactic collisions trigger bursts of star formation and can even lead to the creation of supermassive black holes at the centers of galaxies. Over time, these interactions contribute to the diversity and evolution of galaxies, shaping the universe into the dynamic and varied place we see today. The Great Attractor's role in cosmic evolution also provides clues about the universe's past and future. By studying its gravitational effects, scientists can trace the history of galaxy formation and predict how structures will continue to evolve. Its immense pull reminds us that the universe is not static but a living, changing entity, with structures like the Great Attractor driving its transformation over billions of years. In essence, the Great Attractor is more than just a mysterious gravitational force. It's a cornerstone of cosmic evolution. Its influence stretches across time and space, shaping the formation of galaxies, the distribution of matter, and the very structure of the universe itself. As we uncover more about this enigmatic structure, we gain deeper insights into the processes that have shaped our cosmos and continue to guide its evolution into the future. As we near the end of our journey into the secrets of the Great Attractor, it's time to confront the most intriguing aspect of this cosmic phenomenon, the questions that still remain unanswered. Despite decades of research, the Great Attractor continues to baffle scientists, leaving us with mysteries that challenge our understanding of the universe. One of the most pressing questions is the true nature of the Great Attractor. While we know it exerts an immense gravitational pull, what exactly lies at its core remains unknown. Is it a supermassive black hole, a dense cluster of galaxies, or something entirely different? Scientists have yet to pinpoint its precise composition, leaving room for speculation and further exploration. Another mystery revolves around the Great Attractor's ultimate fate. As it continues to pull galaxies toward it, what will happen to these cosmic structures over billions of years? Will they merge into an even larger supercluster, or will the Great Attractor's influence wane as the universe expands? These questions not only intrigue astronomers but also have profound implications for the future of our universe. The Great Attractor's connection to dark matter and dark energy also remains a puzzle. While dark matter is believed to play a significant role in its gravitational pull, the exact relationship is still unclear. Similarly, how does the Great Attractor interact with dark energy, the force driving the universe's accelerated expansion? Understanding these interactions could unlock new insights into the fundamental forces shaping the cosmos. Finally, there's the question of how the Great Attractor fits into the larger cosmic narrative. How did it form, and what role did it play in the early universe? Is its existence a result of specific conditions during the Big Bang, or is it a consequence of later cosmic processes? These unanswered questions highlight the gaps in our knowledge and underscore the need for continued exploration. In summary, the Great Attractor remains one of the most enigmatic structures in the universe. Its true nature, composition, and fate are still shrouded in mystery, offering endless opportunities for discovery. As we continue to study this cosmic giant, we not only uncover its secrets but also deepen our understanding of the universe's grand design. And with that, we conclude our exploration of the Great Attractor, a celestial enigma that reminds us just how much there is left to discover. If you enjoyed this journey through the mysteries of the cosmos, don't forget to like, subscribe, and hit the notification bell for more fascinating insights into the wonders of the universe. As we bring our cosmic exploration to a close, let's take a moment to reflect on the 30 secrets of the Great Attractor and the large-scale structures that define our universe. From its hidden location behind the Milky Way's galactic plane to its mysterious connection with dark matter and the cosmic web, each revelation has offered a glimpse into the intricate workings of the cosmos. We've uncovered how this colossal structure influences the motion of galaxies, challenges our understanding of cosmic dynamics, and even shapes the very fabric of time and space. These secrets aren't just fascinating tidbits of knowledge, they are crucial pieces of the puzzle that help us comprehend the universe's grand design. The Great Attractor's role in galaxy evolution, its impact on the Hubble constant, and its ties to the early universe remind us of how interconnected everything truly is. Yet, as we've seen, the mysteries surrounding this cosmic giant are far from solved. Its true nature, composition, and ultimate fate remain open questions, inviting future generations of astronomers and curious minds to continue the quest for answers. The journey through the Great Attractor and large-scale structures has not only deepened our understanding of the universe, but also sparked a sense of wonder about the unknown. Every discovery raises new questions, and every unanswered question reveals how much more there is to explore. The cosmos is vast, mysterious, and endlessly intriguing, and the Great Attractor is just one of its many enigmas. If this journey through the secrets of the universe has left you as captivated as it has left us, don't stop here. Share your thoughts and theories in the comments below. What fascinates you most about the Great Attractor? What cosmic mysteries do you think we should explore next? Let's keep the conversation going. And if you're eager for more deep dives into the wonders of space, be sure to hit that like button, subscribe to the channel, and ring the notification bell so you never miss out on our next cosmic adventure. The universe is full of secrets waiting to be uncovered, and we're just getting started.